Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tare, and this is my next video on my series on the Math Lovers book, which I've been running for about a month now. And in case you guys haven't watched these, I'm featuring lessons from my 3-volume series, which I completed in 2022, 3 years ago, called the Math Lovers book. And there's these 3 volumes shown here. Volumes 1 and 2 are both text. Volume 1 is more recreational math. That's the one I'm featuring now. I'm up to chapter 2, section 2.6, actually. And just give a little overview of what's coming up. Volume 2 is a little more academic math, a little more advanced to, I'd say, first or second year undergraduate level. Includes some calculus and some probability theory. And volume 3 is problems and solutions. And you can buy all these on Amazon.com. If you look for my name, David Tare, or the name of the series, The Math Lovers book, you'll find these, and they're available either on paperback or on Kindle. $30 each paperback and $9 each Kindle. I think they're a good buy, so you might want to check them out. But if you don't feel like spending any money, you can watch my series because I'm giving free lessons on all these, on the first 2 books anyway. And like I said, I'm up to section 2.6, which is on the Pythagorean theorem and Fermat's last theorem. This is my second video on that sub-series, and today I'm going to talk about Pythagorean triples. So anyway, let's begin. So what are Pythagorean triples? Well, I think you guys know the Pythagorean theorem. I mean, pretty much everybody learns that in grade school. A squared plus b squared equals c squared, where a, b, and c are the 3 sides of a right triangle, a and b being the 2 legs, the 2 sides that meet at the right angle, and c being the hypotenuse, which is the third side. And what's interesting about the Pythagorean theorem, other than the fact that it's true for all right triangles, I think another thing that's really interesting about it is you have these triples of integers known as Pythagorean triples, and these are just triples of numbers a, b, c, where and they're now all integers, all positive integers, and we also have a squared plus b squared equals c squared. And by virtue of the Pythagorean theorem, that means there exists a right triangle with these length sides. Sides of length A, legs of length A and B, and hypotenuse length C, where they're all integers. And you might think, maybe there's just a few examples. I think most people know about the 3, 4, 5 right triangle. That's the most famous one. It's also the one with the smallest integer values of sides. And it's very easy to check that that's a right triangle. 3 squared plus 4 squared equals 9 plus 16 equals 25, which is 5 squared. And actually, it turns out there's infinitely many of these. This isn't obvious at all, but it was actually the ancient Greeks who not only proved that there were infinitely many Pythagorean triples, but that they actually came up with a method for finding all of them. And there's, I mean, I don't want to get into this. This could be a whole big discussion how to find Pythagorean triples. Actually, I am going to give you a formula that'll allow you to find arbitrary Pythagorean triples. And I'm not going to tell you how to derive it. That's a lot more complicated. But just to give a little overview before I show you the formula, I just want to show you a little table here. This is the first, I don't know, I think it's the first 8 Pythagorean triples. You notice some of them are marked in red, some of them in black. The ones I put in red, I think, are the ones that are what are called non-primitive. The ones in black are primitive. This means that the A, B, and C are relatively prime. There's no common divisor of A, B, and C. No common prime divisor or no common divisor. The GCD of A, B, and C is 1, in other words. And you can check for yourself that's true. 3, 4, 5, those are all. This is what's called a primitive Pythagorean triple because 3, 4, and 5 have no common divisor. GCD is 1, if you like. The next one like that, I think it's alternate. It just happens to be alternate for this table. But the next primitive one is 5, 12, 13. You can check that too. 5 squared plus 12 squared equals 13 squared. You can also check that as primitive. The next one's 8, 15, 17. And that's also a primitive Pythagorean triple. And the next one on this list is 7, 24, 25. And like I said, there's infinitely many of these, and they get big pretty fast. But the ones in red are not primitive, like 6, 8, 10. I mean, those have a common factor of 2. And I think it's pretty easy to see that if you multiply any Pythagorean triple by any integer multiple, if you just multiply each of the side lengths by some positive integer, you're still going to get a Pythagorean triple because if a squared plus b squared equals c squared, let's say a prime equals ka, b prime equals pkb, and c prime equals kc, you're just multiplying all the squares by k squared. So you'll get a prime squared plus b prime squared equals c prime squared. That's pretty easy to see. So 6, 8, 10, for instance, is a Pythagorean triple, is not primitive. And so is 9, 12, 15. I think that's also on this list. And what's the next one? 12, 16, 20, and 15, 20, 25. Those are all non-primitive. And I think those are the only other ones I list on this table. But if you took any multiple of any other one, for instance, 10, 24, 26, which is twice 5, 12, 13, you can keep going like that. So you might wonder how to get all these. And this is a really interesting problem. And I'm just going to give you the formula here. So here's how you do it. You start with three integers, actually. I'm calling them k, u, and v. And they're pretty much arbitrary. K is completely arbitrary. K is just an arbitrary positive integer. U and v are almost arbitrary. The only difference is u has to be greater than v, and they have to have opposite parity, and they have to be relatively prime and of opposite parity. So as long as those conditions are satisfied for k, u, and v, and it's pretty easy to find integers satisfying those properties. As long as you do that, then you can automatically get a Pythagorean triple from these numbers. And here's how you do it. You let what I'm calling a tilde, there's sort of two steps involved. We have to first calculate these numbers a tilde and b tilde. Don't worry about that too much, because the only reason I'm using tildes here is because we might have to switch their order around when we're done. We kind of want a to be smaller than b. We didn't have to define Pythagorean triples the way it's this way. It's customary to do this. I don't know why. It's always customary to say a is less than b. And, I mean, C is always greater than A or B because it's a hypotenuse, which is obviously longer than the other two sides, but it's usually customary to let A be the shorter leg and B the larger leg. So we always start with, here we're starting with A tilde, which I'm defining to be K times U squared minus V squared. I'm defining B tilde to be 2KUV, and C tilde, just C, to be or A to be the minimum of A tilde and B tilde, B the max of A tilde and B tilde, so A is less than B. And finally, C is equal to K times U squared plus V squared. So as long as they satisfy these conditions, this will give you a Pythagorean triple. And by the way, if K is 1, then it's a primitive Pythagorean triple. It's easier to find primitive ones, actually. And usually we don't use tildes. We just kind of let B be the even one and A the odd one. If you do it that way, then you can say A equals U squared minus V squared and B equals 2UV. That's the way it's usually done. But anyway, let me just give you an example here. So let's say K equals 3, U equals 4, and V equals 1. Okay, remember K was just an arbitrary positive integer, so might as well we'll let it be 3. That just means the common divisor for A, B, and C is going to be 3. Well, we can let U be 4 and V be 1 because those are relatively prime positive integers of opposite parity. So let's just see what happens if we pick these numbers. So we just plug in the formulas. A is K times U squared minus V squared. And if you do the math, you end up with 45. And B tilde, that's A tilde, by the way. And B tilde is 2K times U times V, which turns out to be 24. And since 45 is greater than 24, we want to switch them around because we want A to be the smaller one. So A becomes 24, B becomes 45, And now C, finally, that's k times u squared plus v squared. That's a hypotenuse. And if you work that out, you get 51. So this gives you the Pythagorean triple of 24, 45, 51. It's not primitive because k is 3. If we wanted a primitive one, we could have let k equal 1, then we would have gotten, I think, 8, 15, 17. But I think you get the idea. So that's how you find arbitrary Pythagorean triples. And it's pretty easy to see there's infinitely many of them because there's infinitely many possible values of k, u, and v we could have chosen. But this gives you all of them. And I think that's kind of neat. The Greeks knew how to do this. Uh, so anyway, that concludes my video for today on Pythagorean triples. Thank you for watching. Long live math, and I'll see you guys next time. Bye.